Thank you. Thank you, everyone, for being so patient. Again, my name is Sarah Radel, and I'm a graduate student at North Carolina Central University. And today, we're going to be talking about sea level rise on coastal forests in Carteret County. And we're talking about saltwater intrusion, all of these things combined at once. So the correlation between coastal forest loss and sea level rise is of the utmost concern in Carteret County, as it is to many, many coastal communities. Due to the compounding effects of anthropogenic activities, there will be substantial shifts in land cover as a result of sea level rise and saltwater intrusion. This study quantifies and illustrates the loss of forest classifications due to sea level rise and identifies forests most vulnerable to various levels of sea level rise scenarios. As sea levels rise and saltwater intrusion overwhelms Carteret County, coastal forests will be implicated. A land cover change assessment, I don't know why it just changed on its own, but a land cover change assessment was conducted utilizing Esri software, national land cover data, and NOAA's sea level rise scenarios. So let's get started. So one of the very first things I did was obviously I brought in a county boundary. The county boundary was brought in from my organizational account at North Carolina Central University. I don't know why it keeps moving, but it does. All right, so I did create a 3D elevation map of Carteret County. I downloaded the EMs from USGS. This aided in more of a visual reference for me so I could see high elevation and low elevations throughout the county. And if you want, you can copy down the YouTube video. I made a YouTube video that flies over the county in 3D. So it's just for fun if you want to take a look at it. So obviously, national land cover data from 2019 was imported into ArcGIS. An extract by mass was run to extract all the rasters of the NLCD to keep all the data within the boundaries of Carteret County. NOAA's Office of Coastal Management provided sea level rise scenarios of 0, 2, 4, 6, 8, and 10 foot. These scenarios were imported into ArcGIS and aided in the identification of coastal forests lost and coastal forests most vulnerable to sea level rise. A reprojection took place. I needed to reproject NOAA's sea level rise scenarios to NAD 1983 State Plain, North Carolina, FIPS 3,200 feet to correctly locate and display the data. And what we see here is a beautiful, beautiful coastal forest. So this is an image of Croatan National Forest, right? It's located, we have them in Craven County. It's a huge, 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 huge forest. It's beautiful. Stop moving. It's not funny. So, but this forest is so rich in biodiversity. These forests, they sequester copious amounts of carbon. They mitigate, the effects of climate change. They protect inland communities from severe weather systems, sea level rise, and various other things. So these coastal systems, these critical ecosystems, provide a huge service, not just locally, but globally. All right, so this is supposed to move like this. All right, so this is where things start to get really, really fun. So once I ran the extract by mask and I maintained all NLC data, within the confines of the county, I ran an erase. An erase was run on the boundary of Carteret County and each sea level rise scenario. So the erase tool served as an overlay function that removed the features inside of the external boundary. So the results of each erase showed the dissipation of Carteret County with every increase in sea level rise. And this provided new layers of Carteret County boundaries. So with the erase being ran, it's saying that at 0 foot sea level rise, just the land boundaries of 490 square miles. At 2 foot sea level rise, 433. And as sea levels increase further, we see the decrease in square miles of the boundary. The result at 10 foot is 169 square miles total. So this graph illustrates, the loss of boundary square miles per sea level rise. So the boundary of Carteret County, the boundary of the Carteret Erase lost total is 321 square miles. So to spatially display all NLC data within the county boundary of each erase at the various sea level rise scenarios, raster calculations were performed. Raster calculations allowed for the creation and execution of the single map expression using Python syntax, using the raster county NLCD extraction as the parameter in each Carteret erase at the very sea level rise as the mask of all NLC. So this created the rasters of all the NLCDs for every sea level rise scenario. The map that you see here shows an image of Carteret County with all NLC data at 0-foot sea level rise. This image here shows all NLCD within Carteret County at 10-foot sea level rise. So you can see the county's gone. We went from, 535 or 490 to 169. So it's gone. So we've lost a huge amount of coastal forest, agricultural lands, developed lands, wetlands. We've lost a lot. So again, each NLCD was run in raster calculator for each sea level rise scenario. And this was done to extract the various land cover classifications of 41, which is deciduous forest, 42, evergreen forest, 43, mixed forest. The results of the spatial analyst tool raster calculations created new raster images of forest at each sea level rise scenario. Boolean and relational operators were used, 1 for true and 0 indicate false. The above map illustrates the result of the raster calculation at 0-foot sea level rise. So this map shows the result of raster calculations at 10-foot sea level rise. So these are all, the pink are all the coastal forest, left remaining at 10-foot sea level rise. All right, so a fishnet was created that allowed for the breakdown of the county for better forest variations across Carteret County. Each forest raster was then run in zonal statistics, this table, which created new standalone tables, and those standalone tables were joined to my fishnet. The results, and then various calculations were ran, and these results provided important metrics used to conduct spatial analysis, such as pixels per grid, percent of forest per grid, and the percent of change of pixels per grid. Okay, thank you. I don't know why it keeps doing that, I'm sorry. So here are some results after running all those calculations. So at 0-foot sea level rise, I do not want this to move. At 0-foot sea level rise, there are a total of 200,036,788 pixels contained in this map. There are a total of 991 grids contained in this map, and each grid has at least one pixel of one forest. So it's the concentration of forest per grid. Okay. So therefore here, there's 54% of all the grids that are in the county that are coastal forests. Okay. And when we take the fishnet and with the grids and the pixels, there's a total of 500 and, why did it move again? 535 square miles total of coastal forests. So as ocean waters begin to intrude inland at 2-foot sea level rise, there is a total of 232,977 forest pixels within the confines of Carteret County. So at 2-foot sea level rise, forests account for 54% of all the grids within the county, that total 526 square miles. 2% of forest pixels were lost at 2-foot sea level rise, and 9 square miles were lost between 0 and 2 foot. As sea level increases to 4 foot, there is a total of 208,400 forest pixels within the confines of Carteret County. At 4 foot sea level rise, forests account for 52% of the overall county grids, total of 471 square miles. Overall, at 4 foot sea level rise, 12% of forest pixels were lost and 64 square miles of forest were lost between 0 and 4 foot. At 6 foot sea level rise, there is a total of 170,156 forest pixels within the confines of Carteret County. At 6 foot sea level rise, forests account for 46% of all the grids within the county, totaling 384 square miles. There is a deficit of 28% of all forest pixels, and we have lost 151 square miles of coastal forest between 0 and 6 foot sea level rise. At 8 foot sea level rise, forest pixels were reduced further to 130,101 pixels. The total percentage of forest at 8 foot sea level rise is 39%. That total 294 square miles. 294 square miles. So 45% of all forest pixels were lost, and we lost a total of 241 square miles of coastal forest between 0 and 10 foot sea level rise. So here we see a funnel chart. You probably can't see that. This is the average number of pixels per grid at each sea level rise scenario. So, at 0 foot, there is a total of 239. There's an average of 239 pixels per grid. And at 2 foot, it's 235 pixels per grid. And at 4 foot, it's 210, 6 foot, 171, 8 foot, 131, and at 10 foot, 105. So this graph here shows the square miles of coastal forest at various levels of sea level rise. So there's a total loss of 292 square miles of coastal forest between 0 and 10 foot sea level rise. This keeps moving on me. It's rushing me. It keeps moving. I'm sure I skipped 8 foot somewhere. So spatial analysis was then conducted further. So where does the vulnerability come in? Where does this sea level rise? Where does saltwater intrusion, where does all this come into play? So spatial analysis was then conducted further to obtain the forest most vulnerable to sea level rise. When I say most vulnerable, yes, I do mean increasing levels of ocean waters that are coming in. But what I also mean is the vulnerability to saltwater intrusion itself. Initially I had run a 50-meter buffer in my data. I said, okay, I'm gonna run this without a buffer, and I'm gonna run a buffer of 50 meters from the shoreline, because 50 meters from the shoreline is that zone of dispersion where freshwater meets saltwater. Whenever I compared the non-buffer to the buffer, they were exactly the same. They were the same, so there was no reason for the buffer. They produced the same exact thing. So I can tell you that the most vulnerable areas of between 0 and 2 foot are the exact same 50 meters from the shoreline. So these areas that you're seeing, I don't know why it's showing 6 foot, but these areas that you are seeing are areas of coastal forests that are most vulnerable to sea level rise. So spatial analysis was then conducted to obtain the forest most vulnerable to sea level rise at 2 foot, 4 foot, 6 foot, 8 foot, and 10 foot. And this was done by subtracting the control forest pixels from each forest pixel percentage per grid at each sea level rise scenario. So results of these calculations show coastal forests most vulnerable to saltwater intrusion and sea level rise. So here at 2 foot, there's a total of all these grids, there's a total of 9 square miles at 2 foot sea level rise that are vulnerable. Further spatial analysis conducted further spatial analysis showed that at a 4 foot sea level rise, 64 square miles of coastal forest are most vulnerable to sea level rise. So we know saltwater intrusion is happening. We can see coastal forests transitioning, but now I can say, this is where. This is where you're going to start seeing those changes. As ocean waters continue to intrude further inland at 6-foot sea level rise, there's a total of 151 square miles of coastal forests that are vulnerable to sea level rise. So at 8 foot, there are 241 square miles of coastal forests that are most vulnerable to sea level rise. And finally, at 10 foot, there is finally at 10 foot. That's fine. Believe me, it's whatever right now. But finally, at 10-foot sea level rise, these are the coastal forests that are most vulnerable to sea level rise. And this is a total of 292 square miles of coastal forests that are vulnerable to sea level rise between 0 and 10 foot. So we finally now have something that actually shows us where we're going to start seeing these changes. All right, so NLCD and NOAA sea level rise scenarios were leveraged to conduct spatial analysis to identify and quantify forest loss and forests most vulnerable to sea level rise. The total forest lost and vulnerable, they do equal out. You know, at 0 to 4 foot, we have 64 square miles of forests most vulnerable and lost. At 0 to 10, the sea level rise, we have 292 that were vulnerable and 292 that were lost. So that tells us what's vulnerable, we're going to lose. We're losing it. So those should balance out unless there are some mitigation and resiliency measures that take place that we can use some type of buffer to help mitigate that. These numbers are going to stay the same. So some next steps in my research is to connect the impacts of sea level rise to societal impacts and to, Doug, take this spatial analysis framework and create a forest loss model. So, well, so the correlation between coastal forest loss and sea level rise does concern Carteret County, North Carolina. A land cover assessment was created using Esri software to encapsulate data representing the extent of sea level rise and its explanatory factors. The purpose of this study endeavored to achieve a land cover assessment to quantify and map sea level rise that assesses and evaluates forest changing due to sea level rise. In this assessment, the first law of geography, known as Tobler's law, holds. Everything is related to everything else, but near things are more related than distant. Therefore, as sea levels rise, due to the compounding effects of exacerbated anthropogenic activities, there will be a significant loss of coastal forest due to sea level rise. Thank you. Of course you do. Yes, hit me with it.
Okay, you're looking at the elevations and the forces of the land that have that elevation, and taking consideration to the effects on the tourism. Say if your elevation was 3 feet and the sea level rise came up to 3 feet, would that impact the forest land that you're talking about?
You know, I don't think, you know, obviously things that have a higher elevation, but, you know, when saltwater, you know, comes in, I think it inundates that soil, that salinization, and it changes the composition. So they might not transition as fast as those that are in like direct exposure, but I think over time, because they can only have like short period, but I did not consider that, and I should. Thank you. I should look at that.
I didn't think one of my associates in the
They thought of that. Yeah, I didn't think of that because I just thought of the salinization of soil. Because when I look at agriculture, I think, okay, we have the salinization of soil, and these are things that we can do. And we have these root systems, and we have groundwater. I'm trying to think of all these things. So that will go into the model once it's created. Thank you. Yes.
Related question,
Yes.
And if they were
Right, there, as of right now, there is not a map of ghost forests in Carteret County. But if there would be a way, absolutely, do a change detection, yeah, that would be really, really helpful, because this NLCD was from 2019. Yeah, so that would be really helpful. Thank you. Yes.
The current model is what I have, two, but you could do something, you could go above that.
Yeah, it's like, it's only 0 to 10 foot. That's what the sea level rise scenarios that NOAA has put out. If they're expecting higher increase in sea level rise, I haven't seen that.
No, they go beyond, I think, 2199.
Yeah.
But I was only using the term that they're going to 2100. I would expect to lose that one, so.
I know. And you can't really, I mean, honestly, when I had tried to put time to this, I got really nervous, even looking at time. It's like, you can't really say because, 6 months ago, we were going to be at between 2 to 4 foot in, 2050? And now they're saying like 2040, 2035. So it's like time is such an issue. I don't want to go down that rabbit hole. It scares me.
Yeah.
It's a scary rabbit hole to go down. Anybody else? I, I have not. Thank you. I should do that. It's really important. Thank you. I have not. Honestly, in Carteret County, and there could be more. The ones that I only know of are the ones at the Pine Knoll Shore Aquarium, and then we have a living shoreline at Carteret Community College. I'm not aware if there's any others that they have out there, but I think that, in my thesis, I have my mitigation and resiliency where I incorporate living shorelines and halophytes so we can combat metals and, high osmotic stress and stuff like that. Definitely to try to build resiliency and mitigate, and even to show resiliency economically where you could use these because halophytes are edible and we could change the palate and we can incorporate these foods and be sustainable within the county. You're scared. It is.
Yeah, it's what you don't see.
Yeah.
How easy would it be to change this?
It's very easy. It's very simple. It's very easy. I have, I'll scroll down right here. One thing that I have to do, I can put this, I use this with this 123, the model builder in ArcGIS. I can take, this is the first time I've ever done anything like this, right? If I were smart, I am, but if at the time when I was doing it, if I would have just made one big model, I could call it a model, but I didn't, so I have to call it an assessment. But I have all these built, and they are all together, and it's as simple as, if I'm assuming, it's as simple as just going in and joining them into that, and then that model is created. It is self-replicating. I've ran it not just on coastal forest, I've ran it on agriculture, I've ran it on developed medium to high, I've ran it on wetlands, I ran it on the different classifications in Carteret County and did an assessment on all those classifications.
Where did you get your elevation?
I got my elevation from USGS. There was a 1 meter from USGS with LiDAR.
Do you think that you would have more refined, more accurate results using a more up-to-date LiDAR source for that area?
Yeah, I do. I do.
Yeah, the only thing like you have to require some
Yeah.
They usually learn and they get to a lot, but with the long short grid, it ends up in the mile. They can keep it in a mile, and it's like 50 miles long. So, like, yeah, so that what happens is the native piece is like a little bit more, and so they'll learn there, which is really like gradually and
Yeah, we do it like once a week and then.
but it doesn't stick. It's like long short grid, which is so like waves come in and out like this, but then they also travel down the beach. It's like such a cascade and
Well, yeah, and another topic to bring up with that, since you brought it up, is we can talk about dredging. You know, it's, what is the impact of dredging, right? That is not real. This actually contributes to this,
right.
right? So there's a lot of different things. I mean, we carbon for recycle oyster shells. We have parking, we try to instill, you know, the shoreline, and we have living shorelines, and we try to do all these things, but she's right, everything just goes that way, and we're left with nothing. Yeah.
Thank you, Sarah.
You're welcome. Thank you, guys.
Thank you guys so much.